Next problem is to find the equivalent resistance between the points A and B of the network shown in the figure. Each resistance is equal to R. Here we will solve the problem using the symmetry of the figure and then taking the mirror images with same direction of current and magnitude. Here you have to find the equivalent resistance between the terminal A and B. So we connect these two terminals by a dashed line and make a perpendicular bisector of this line AB. This perpendicular bisector is our line of symmetry across which two parts are mirror images of each other. Now suppose current incoming is at a terminal A is I. This have three outlets, so these three currents are suppose I1, I2 and I3. Now taking the mirror images about the line of symmetry, current I1 is in AD. Its mirror image across the line of symmetry is CB. So current will have the value I2 in same direction. Current I2 is in branch AO. So we will have the current I2 in its mirror image part, that is OB in same direction. This is I2. And third one is I3, and I3 will also have the same direction and the magnitude. So at terminal B, these three parts, this is I1, I2 and I3, these totally sum up and comes out with net current I. Now we have to mark the current in other part of the resistors. Here this I1 reach at the D, this is I1, and suppose it break in two parts, this is I4 and another one is I5. Because at O the current incoming is I2 which outgo and go to terminal B, and I5 come at O and this will take the path OC, and I4 will come using the mirror image about the line of symmetry. This will have the same value I4 and same direction of current. OC will also have the same value of current in the same direction. Therefore we can see here one important point, that this I5 and I5 are same and this passes through O without any change. Similarly, I2 in AO is same as in OB. This also passes through O without any change in the value. That means we can see that this AOCB and this DOC can be treated as non-connecting points. Therefore, we can redraw this figure as, that is, this is O. So we can write here, this is one of the resistance. This is another resistance, second. This one is our third resistance. Another one is fourth resistance. And then here is a resistance R. This is not connected at O, which we can treat as, and here it is a resistance R. Similarly, a resistance R which is not supposed to connect at O and it is connected here with that point C. This value is R. Effectively the resistance is this, and we have to find the equivalent resistance between A and B. Current is coming at A and going out of B. So now the problem gets simplified because these two resistors are in series, so effectively their value is 2R. Also these two resistors are in series, this effective value is 2R. And we can redraw this figure as, it is one of the resistor, this is another resistor, this is a resistor R, and it is a resistor R, and here there is a resistor 2R, and similarly there is a resistance 2R, and we have to find the effective resistance between these terminal A and B. So we can see here this R and 2R in parallel, so their effective value will be 2R into R by 2R plus R, that is equal to 2r by 3. Their effective value is also 2r by 3. And this 2r by 3, this r and this r, these three resistances are in series. So we can write that this is terminal A, this is terminal B. There is a net resistance connected 2r by 3, and it is a parallel with effective value of the r plus 2r by 3 plus r, which are in series. So it is giving 2r by 3 plus 2r, or we can write it as 8r by 3. So 8r by 3 and 2r by 3 are in parallel. So R equivalent will be is equal to 2r by 3 into 8r by 3 by 2r by 3 plus 8r by 3. So we can write it as 16r into r by 9 divided by, this is 2r and 8r, 10r by 3. 1 3 get cancelled, 1 r get cancelled. It is equal to 16r by 3 into 10, that is equal to 16r by 30, or we can write it as 8r by 50. This is the answer.